Okay? All right. So in a world where everything revolves around communication, session types have turned out to be humanity's last asset. Under the fearless leadership of the late Kohei Honda, generations of researchers have investigated their meta theory, and they actually also built into existing languages like Java and Haskell strongly typed communication protocols. In return, they received type and communication safety, and for some versions of the calculus, like you've seen in the previous talk, you got deadlock freedom. All right. Although Garrett already mentioned GV, the calculus of which the syntax I will be using most of the time, I'll show you a short GV program, which is type-safe streaming of a list, just to get you into the mood. So here we have a list data type in syntax reminiscent to Haskell. And here I use a mu-free notation of a session type using explicit recursion. So it's called list server. It also has a branch type. And here we have branch labels, like you've seen in the previous talk. And here in the last line, after I've received a cons message, I expect to receive an integer, and then I recurse on the list server. So, and because I will look a little bit more, and there's recursion on the list server. All right. Right. And as I will show you a little bit more code, I'm also showing you the code of this list server. So essentially, it's a recursive function that takes a channel C of type list server as its argument. Then it will first destruct on the branch type, this case on C. And let's only look into the cons case, into the second case. In that case, we get here in the branches, we get the depleted channel after the cons has been read. We get that here. And then we receive first the integer. As you see, we are continuing here. We're following here the session type sort of synchronously with the code. Then we got a new channel, C1. From that channel, on that channel, we recursively invoke this list server, which then reads the entire rest of the list. And finally, we put the return value together. And hooray, we received a list from somewhere else. That was easy, wasn't it? So great, we can use session types to transmit list structures. Okay, let's try something else. In functional programming, everything you try first, you try it for lists. And then you say, now I want to generalize it to trees, right? Let's try that. And let's be modest and look at a very small, very simple binary tree type. So I've chosen a binary tree type where the leaf doesn't carry any information and where all the juice is really in the node, in the middle of the node. Well, we have a left tree and a right tree, as you can see it in the picture. And now the task that I want to put session types onto is I would like to serialize that into a stream of basic data, namely just sequences composed of node and leaf and whatever, integers in this case. And I would like to write a deserialization function that is able to resurrect the tree from this stream. And, it's actually easy enough to write the code by more or less following the pattern that we've seen for the list server, right? So whenever we see a leaf, so C is the channel. Whenever we see a leaf, we return a leaf. Whenever we see a node, then we recursively read a tree, an encoding of a tree. Then we receive the data value, and then we recursively receive the right tree, and we put it back together. All right, seems easy. What about its type? I should say one more thing. To make the task interesting, I restrict myself here to communicate base types. Right? So if I had a primitive that says transmit a tree, I would kind of get rid of the problem immediately. Also, I'm using first-order session types because I'm interested in, real communication in a distributed system, say. There is a solution using channel passing where you would create a new channel and pass the channel to the other party, but in a real communication setting, that would be quite expensive. So I would like to stay on one channel and only transmit base type values. All right, and I'm interested in a typing. So what should the typing guarantee? So the typing should guarantee that I don't have any ill-formed stream. Yeah? So if the stream contains, the stream should never contain a sequence first node, then 5, then leave, because that doesn't correspond to that cannot be resurrected into a tree. Similarly here, we have node, leave, 5, and there's no right subtree following. So this stream ends prematurely. I would like the type system to rule that out too. And here we have leave, leave. Well, that looks like the stream has extra elements. So I don't want such streams either. So the typing should guarantee that none of these problems should happen, as you would expect from a nice typing. However, there's a little problem. So here I've put up again the list server type that you've seen in one of the first slides. And now I'm showing you a graphical depiction of that. So essentially what you can see, what you can essentially do for any first-order session type, you can transform it into a finite state automaton. So essentially here, this starting state, that stands for the list server. And well, here the nodes, they stand for the let's say operators in the session type. And what you see on the arcs is the communicated values. And now I can ask, what kind of languages do I get when I follow traces in this automaton from start to end? Everybody of you knows that. I get a regular language. Yeah? So whenever I have a session type, which only has finite communications, then I get, well, it corresponds to such an automaton, and I get a regular trace language. Well, so there's a little bit more behind it. So you get a omega regular language, but let's not get into that right here. Now, that's true for any first-order session type. Now let's look at the traces that we would get from raised tree. Yeah, you saw the code. So the code says either you send a leaf thingy, or you send a node thingy, then you recurse, then you receive an integer, and then you recurse again. That looks quite like a context-free grammar to me. And indeed, the trace language that you get out of this is a context-free language, which means sort of that there cannot really be a standard session type that is able to guarantee type safety for our raised tree function. Yeah, for example, it cannot be typed in this in the GV calculus that Garrett also mentioned before. Okay, so that was our motivation to study something that we call context-free session types, and it looks like it's just a tiny modification in the syntax, and I'm only showing you one part out of it, namely this one here. In a regular session type, you always have this communication hardwired with its continuation. Yeah, so whenever you send a value, then you immediately have to specify what happens afterwards, what happens next. Similarly here for reception. So all you have to do in order to get to a context-free formulation is to rip off the continuation, and now we have types bang B and question mark B that just stand for the act of sending or receiving a value. But then you need two glue operators, namely the semicolon, that sequence that is sequential composition of two sessions, and skip, which is sort of the empty session. And what you get out of this is, whereas in regular session types, you are restricted to being tail recursive and to encoding serializing list-like structures, in this context-free setting, you have unrestricted recursion. And so here I put up the list server type and a proposed type for the tree server. side by side so that you can see the difference. So, well, in the nil or leaf case, well, in both cases there is nothing interesting. Only here it's end, so that well, here it's you say end because that's the end of the communication at this point. And here for the leaf you just say skip. You do nothing, but the leaf may occur somewhere nested in the tree, so you can't just say end and stop transmitting. For the cons node, well, we saw you receive an integer and then the list server again, recursively. For the node, when you see a node here, well, you first do the tree server recursively, then you receive an int, and then you do the tree server again. And notice the semicolon in between. And well, now there are a couple of ways to serialize the tree by just taking different sequences, by permuting the sequence of arguments here. In both cases, you see that the types fit, the session types fit the shape of the data type, and they also fit in nicely with the code. Unfortunately, the meta theory for the context-free sessions is a little bit more involved. And I'll only give you a few glimpses out of that. The paper contains a lot more of that. So let's just, oh, great. So let's look into some of the requirements for the meta theory. So one thing, I haven't yet shown you the typing for race tree, right? I've given you a proposal for what the stream type looks like, and it looks great because it more or less mimics the data type definition. But I haven't shown you a type for race tree. And indeed, it turns out to be a slightly non-trivial exercise to do that. Let's consider the top level. At the top level, we would like to have a race tree to receive a tree server, and then it should return a tree and a depleted stream. And for the depleted stream, let's say we'll use skip. So on the top level, you would expect a type like this. Race tree takes a tree server, and then a tree paired with this depleted channel. And I'm using pretty much the same symbols as Garrett, fortunately. Unfortunately, if you go down into the code and look at the first recursive call, so this is these are 3 lines from the code. At the point where we have selected the node in the code, we have a channel of this type. It starts with tree server, right? So after we know we are in the node, then we say recursively read the left tree, then read the number, and then read the right tree. So C0 has this type. Now, if you look at what should be the type of race tree at this point, it doesn't match this type here, right? So here C0, it doesn't have type tree server. It has type tree server, semicolon, question mark in, semicolon, tree server, and maybe some other stuff behind it, which we don't know. And then the output will be tree. Okay, that's good. But then it says, well, not just int, but semicolon, tree server, and so on. What's your suggestion? Polymorphism, yeah. Polymorphism to the rescue. Very well. So fortunately, there's a polymorphic type for a race tree, namely this one here. For all A, tree server, semicolon, sorry, for all alpha, tree server, semicolon, alpha, to tree cross alpha. And then, essentially, alpha can be properly instantiated at different points. Namely, initially, you would say, for the outermost call, you would have alpha is equals to skip. Or maybe if you use the channel after reading the tree, you may want to instantiate it differently, okay? And then you essentially get tree server, semicolon, skip, blah, blah, blah. That's not quite the type that we had expected. So we need this kind of equivalence in the types. Yeah? So we would really like type server, semicolon, skip to be equivalent to the type tree server. Sorry. All right, and I'll come back to that equivalence on the next slide. And on the other, for the other, if we instantiate alpha to question mark in, semicolon, tree server, and then some beta, then that also fits at the other call. And now I should have a call out, but somehow I missed that. So now, this was the typing that I proposed for race tree, right? And this is the type of the recursive call in the body of race tree. It's an instance, right? It's not at this type, but it's an instance of the type. So you have polymorphic recursion. For the second call, you don't need an instance, but in this case, for the first call, you need polymorphic recursion. So, all right. Okay, but I wanted to get back to the type equivalence thing. So now you've already seen that in a small example that we need some type equivalences in order to do type checking. One of the type equivalences was this tree server semicolon skip equals tree server, but there are a couple of more of them. So as I already mentioned, we need this type equivalence in order to do type checking. And in order to have a decidable type checking algorithm, the foremost thing is that the type equivalence must be decidable. Otherwise, we would be talking, we would be just talking, right? We could never implement it. All right, that's a bit annoying. Yeah? So it turns out that these context-free session types, in order to be useful and in order to be sufficiently flexible in typing code, they need to have a non-trivial equational theory. So one thing is that recursion is silently unfolded, which is called equi-recursion, but that was already the case for regular session types, and we know how to deal with that. But then these operators, skip and sequential composition, they form a monoid, and indeed, during type checking, we actually need the laws. We need the identity laws, and we also need associativity. And you can see in the paper there's a long development which tells you at which places all these laws are needed. Furthermore, you need distributivity of composition. Yeah, so you need to be able to pull this continuation, so to speak, inside of branch or choice types. And that's also in the paper, the example for that. So that looks quite complicated. So how can you find a decidable theory for this sort of type equivalence? Now you might say, okay, there's equational unification. Yeah, there's equational unification with associativity, identity, and so on. But unfortunately, this is not about trees, but we have recursion, right? So we have infinite trees. So we need unification with these laws with infinite trees. And that looks a bit more annoying. Yeah? So how do we decide that? Actually, it took us a while asking a few wise men. And then at some point, we found a strategy that allowed us to come up with a good definition for type equivalence and also finding proof for its decidability. So let's try to define it. So let's say we have types T and T prime. So the trick is really to find somebody who remembers work on process algebra from 1988. Yeah, in 1988, Bergstra and Klopp started a long strand of research on process algebra, and the system that they proposed back then was basic process algebra. Yeah, so you can find details in the paper. Let's not go into detail with that right now. The nice thing is, the nice thing is that their structure is fairly similar to the type structure that we have in context-free session types. And indeed, in the paper, you'll find a function that translates a session type into a BPA process, into an equation system of BPA processes, to be precise. Now, on BPA processes, there is a well-defined notion of equivalence, namely bisimulation, that has been explored by these process algebra guys. Thank you. So now what do? Well, we just pull it back. Now we say our types, T and T prime, they are type equivalent if their translations into BPA are bisimulations. Okay, good. Then another result helps us, namely there is a paper by Christiansen, Hüttel, and Sterling from 1995. They have shown that bisimulation for BPA is decidable. And since our type equivalence is defined in terms of BPA bisimulation, we have decidable type equivalence as well. And because of the way that this algebra is structured, we have all these laws as well. So in the paper, you'll find proofs that all these algebraic laws hold. And that brings me to the conclusion. So I've shown you our proposition for context-free session types. They compared to regular session types, they give you a, let's say, provable gain in expressiveness. Well, you have context-free trace languages compared to regular trace languages. The price is that there is a significant complication in the meta theory. But it's only, the complication is only in the part that I've shown you. The standard results, namely type safety, communication safety, and so on, they work just as they did before. Also the operational semantics, which we also put into the paper, and which some of you have already seen on Sunday, thanks to David, that can all be taken over from GV. So the main thing is to have this type equivalence. And it applies to practical example, namely type-safe serialization, interactive exploration of tree structures, and there's a couple more of that in the paper. And with that, thank you.
All right, time for questions.
So you had a slide at the beginning on, oh, this is a low-level code, so I'm not doing this and that. Mm-hmm. And in retrospect, I understand that it was carefully designed to avoid having to handle the full pi calculus. Mm-hmm. But is that a choice that you can continue making going forward? Like, is someone going to say next year, oh, we actually want channel passing, and therefore our types must be more powerful processes? Mm-hmm.
Okay.
How do you see the future?
Okay, so the reason for choosing this particular setting is to have a low-level solution where you have one channel which you can reuse in a real communication setting. So I think I mentioned that you can do this. I mean, as in pi calculus, you can do it with channel passing by creating a new process. In pi calculus, it doesn't cost you anything, because it's just a name that you create. But in reality, that's probably too much. What I envision is that you can use it to write typed serializers and deserializers for things like JSON or XML or stuff like that, which I think is possible, but we haven't tried it yet.
All right. Any more questions?
It seems like, Michael Anzinius, University of Birmingham. It seems like there should be a channel passing interpretation of any context-free session type just by replacing skip with 1 and the semicolon with tensor or with output. Is that accurate?
Oh. I would have to think about that. Let's talk about it offline.
Okay, fair enough.
All right, and there was one more question, right? Yeah, there.
Ren Romano from Google. So I guess kind of the obvious question, if you had to move from regular languages to context-free languages to get these data types, have you thought about in the future needing to go to even more expressive forms of grammar in order to serialize and deserialize other more interesting data types?
It's an interesting question, but I think that decidability will speak strongly against it.
Yes.
All right. Last question, yeah. Phil.
Phil Wadler, University of Edinburgh. You mentioned you have communication safety. I couldn't tell if you intended that to include deadlock freedom or not.
We didn't really prove it for this system. In GV, which it was built on, you have higher order sessions, and therefore I believe you don't have deadlock freedom.
Well, it depends on which variant of GV you look at. If you look at the one in my paper, which was called GV because it stood for good variation.
That's true.
Else it did have deadlock freedom.
I was thinking of the original paper.
Right.
I think in this work we talk about first order. I think, but we didn't prove it that it is deadlock free.
Future work.
Yes.
All right. Let's thank Peter and. And this concludes the session.